I guess today we're actually going to jump ahead and cover linear regression first and then circle back to the bias variance decomposition, just because I think conceptually it makes a bit more sense to talk about linear regression or talk about bias variance after we've covered the linear regression objective. In terms of some basic announcements, we released homework 1 last week. It's going to be due on Tuesday at 5 p.m. There's going to be, I don't think the office hours are on the website yet. The head TA is coordinating that, but it should be out today, and we should have 15 or so hours spread through Wednesday to next Monday. And it's a mix of virtual and on-site hours. So in general, we recommend going to the earliest possible ones you can attend because we'll probably get busier. And I think we'll have TAs who will be in charge of handling Piazza questions on the homework as well. Any questions on the announcements? Okay, cool. Let's jump to linear regression and then we'll circle back later. All right, so up to this point, we've primarily been talking about classification, like when you have a bunch of different classes you want to consider, and the goal of your machine learning algorithm is to output which class the new data coming in belongs to. In this lecture, we'll primarily be focusing on regression, which is where you're trying to predict scalar value targets. So one example is trying to predict stock prices. And we're focusing on a linear function here, so something that's a linear function of the inputs. Does anyone have examples of other regression tasks that might be interesting? So what are some other machine learning things? Yeah.
Logistic regression?
Right, logistic regression. Yeah, I guess I'm looking for examples of tasks. So like predicting the stock price, or yeah, what else might we consider? Yeah.
And do research related to dielectric elastomer actuators or trying to predict the electrical breaking point? So essentially like a voltage value at which the system breaks down.
Cool, yeah. So yeah, I guess there's like many possible examples, right? So you can predict electrical breaking point. What is something else we might want to predict?
Just linear or
Any regression problem.
Oh, not just linear.
Yeah, I guess like I'm looking for examples of regression problems generally. So like, what is a problem that's potentially interesting to you? Yeah. So.
The frequency of a voice or like a sound.
Yeah, that's good. So like for speech recognition, we could predict frequencies. Yeah. And I guess a pretty canonical example that people often allude to is predicting house prices. And I guess in general, it's probably helpful to ground a particular use case in mind because it sort of makes the problem a bit more concrete rather than just abstract math. And then as you go forward, like working on different projects, it's good to just have ideas of how these algorithms can be useful. Yeah.
For architecture, are we like assuming that the underlying function is a linear function of the inputs, or could we like prove it in some sense?
We don't make that assumption. So what we're doing in this case is we're making this assumption for our modeling class, but that's not what the true data necessarily comes from. Okay. So this is actually like the first lecture of basically 3 or 4 part series where we're going to dive deeper into this approach of ML where we specify a model. So today we're focusing on linear models, but in the future we'll talk about neural networks. We define a loss function that defines how well we do on the data using our model, and then we try to learn by updating the model over time. We'll also discuss the concept of a regularizer today, which is the idea that you might want to decrease the weights of your model. Perhaps like a simpler hypothesis is better. And then today we'll also start discussing optimization algorithms. So how you go about training your model using gradient updates. Okay, so just a refresher, in the supervised learning setup, we have our inputs, which consists of vectors of features. We have our targets, which are real values. And then in general, we assume we have n data points. So today we're primarily going to be working with n by d matrices, where we assume each row of our data matrix or design matrix consists of one training example. So x1, x2, all the way to xn. And then our goal of lists and coming lectures is to try to learn this mapping from our data matrix to a vector of predictions, which we hope are close to the actual labels that we're given. So we're trying to learn the function f of x. And then today we're specifically focusing on the linear model, right? So we're assuming that the goal is to predict a linear function, the features, and the way we write lists is y equals f of x, where if our features are x1 through xd, I guess each of these are scalars. We assume our function takes the form w1 x1 plus w2 x2 all the way to w dxd. So you can write that in summation notation as well. And then there's this idea of a bias as well. So the bias is something we add to make sure that by default, if you have a 0 in all of the feature values, we don't necessarily have to predict 0. We can actually have a default prediction for when the feature values are 0. So I guess to be a bit more concrete here, suppose we're trying to predict house prices. And our features might be the number of rooms and something like the square footage or like the area of the house, right? So if we end up learning a linear model which places, I don't know, some numerical value on the number of rooms and some value here, what this is saying is our linear model is saying for every increase by 1 in the number of rooms, then our prediction is going to increase by 100. Right? Can someone tell me like how you would interpret number of rooms being 0 and square footage being 0? What would that potentially mean? Yeah.
It means that they don't affect the outcome.
Right. Yeah. If w1 equals 0 and w2 equals 0, then that means they. But I guess like, what happens if x1 and x2 are 0? Yeah, up there.
We get the constant fee, which is like the minimum price, how to map it out.
Yeah. So that might just be like the estimate of the land value itself. Like if you had no actual house, then that's what our linear function approximates the cost of the land to be. Yeah.
If the weights do end up going to 0, you can't further update them because the way you update the weights is through variables, right? So if the weights are 0, you can't.
Yeah, that could be potentially problematic. Yeah, so generally you do want to initialize your weights to be non-zero, and then I think it's not a problem. Yeah.
We need to normalize them.
In linear regression, I think it can make the learning problem potentially easier, or especially in neural networks later on if you normalize the features. But you can imagine if you don't normalize, you might just learn 10x for one weight versus another one. Yeah.
So, it's also possible for, not in this case, but it's also possible for the values to be negative. So let's say, for example, like if I'm hosting a party, then the amount of dishes let's say W0 is like a set amount of dishes. If W is positive, then that means I'm ordering more pizza than if W is negative, then I'm ordering less pizza. Would that be an assumption?
Yeah, absolutely. Yeah, you can have negative weights as well. So there might be things like proximity to a freeway or highway that affect the value of a house as well. Yeah. Any other questions on this basic setup? Okay. Cool. So this is just how the function is defined, but we want to go about basically measuring how good our current model is doing. So the way we do that is through something called a loss function. And it basically specifies how badly the algorithm's prediction is versus the ground truth target. So the most common loss function we use for regression is something called the squared error loss function. So here we have y, which is f of x. So it's what we showed on the previous slide. You have some model that generates a prediction on your data point. And then we basically take the difference between that and the actual ground truth value, square it, and divide by a half. And the 1/2 is really just for mathematical convenience, because when you take the derivative, the 2 and the 1/2 cancel out, so it's nice. And we don't care about just this loss function on one single data point. We care about the performance across all of our data points. So in general, we're going to consider the empirical or average loss on our training examples. And you can express it in summation form here. So this is the general form for any method of predicting. And then you can also substitute for linear regression what the form of the function looks like. Yeah.
Why do we square the difference instead of taking the absolute value?
Yeah, that's a good question. So it's mostly, I guess, a matter of convenience, and this approach tends to work pretty well. So you might imagine we want to penalize errors that are really far off more, and then the squared loss is a natural way of doing that. It's okay. We'll go through like the math of how we go about doing updates pretty soon. One other thing that you might want to consider is sometimes you think certain data points are more important than other ones. Turn it off. Yeah. And then in that case, you might want to consider putting weights on your data points.
Sorry, I don't know what happens to my computer.
Okay, that's okay. Yeah, don't worry about it. So you can consider putting weights CI. So by default, the weight on all the different training examples is going to be equal to 1. But you could imagine weighing certain data points more, which you perhaps have more confidence in, or you care more about getting correct. Okay. So next we'll talk about vectorization. So this is something we sort of alluded to in the first lecture, which is when we want to express these computations to a computer, it's often much more efficient and sometimes clearer for us as well to write things in vector form. So rather than writing things out in summation notation or with for loops, we want to go about trying to write this as a single vector expression. In general, vectors in this class, I don't think I've mentioned this before, will try to highlight with a boldface lowercase letter. So these are vectors. If you're ever confused about the dimensions of some object, just ask, because I think it can be potentially confusing at times. But essentially what's going on here is if we have our weight vector and a vector of feature values for a particular data example, then we can go ahead and express the prediction in this vector form, right? So y equals w transpose x plus b. And on a computer, you can do this using the NumPy library as mp.wx plus b. Does that make sense? there's often a trick you sometimes see where rather than writing out the b's separately, we can potentially write this out in a single expression. And the way you go about doing that is you augment your feature matrix with a column of ones. Or I guess in this case, we're going to put in the original x plus a 1. And we do this for every single feature. So if you add a 1 and basically increase the dimension of your features by 1, then this ends up working out nicely because you can just interpret the very last feature as the bias component. So you don't need to add a plus b. And there are benefits of vectorization. So the first is it's a lot simpler and more readable. So you don't need additional dummy variables when you're writing out a for loop. And in programs like Python, it's actually much more efficient because Python has a lot of overhead to make things appear nice and easy to program. But if you can call the underlying C libraries or use specific libraries for dealing with vector operations, you can often do your computations much faster. Right? So in general, when you're writing code that goes in production or something, you would use a library that does the underlying operation quickly. Yeah.
Is sum of squared errors a type of loss function, or is the opposite true?
Sum of squared errors is a, I guess, do you mean the loss function? Yeah, you can, it is a type of loss function.
Okay.
Yeah. And one thing, I guess, to mention here is it's when you're deriving things by hand, especially initially when you're just learning about all this stuff, I think it's still often useful to write things out in scalar notation and work through examples like on problem 6 of the math diagnostic quiz. But I guess eventually you'll want to sort of get to the point where if you see an expression like x transpose ax, and if A is symmetric, then you know the gradient with respect to x is going to be equal to 2ax. Initially, you write this out term by term to convince yourself it's true, but then later on you just can abstract that knowledge away. Questions on vectorization? Yeah.
So you talk about how this is faster if we use vectors rather than like adding stuff up. So if you, can you please go back to that?
Yeah, of course.
So does that mean we like to optimize like runtime in Python? Let's say we should always like augment the matrices so we don't have to plus a b on the end because it's faster.
Yeah, I think if you're using a library, it can sometimes like compile the graph in a special way that the plus b doesn't end up mattering too much. The bigger problem is probably usually with for loops. So if you see a for loop in your code, that's probably a sign that it's like 100 times or perhaps even worse, slower than it needs to be.
So if we just have the plus b, it's not that bad. But if we have a for loop, we should probably think about using a library.
Yeah, exactly. Okay, so yeah, this is just reviewing our setup again. You can, again, imagining putting an extra column of ones and just appending this to our feature matrix. It's also known as the design matrix. And then we want to compute the squared error cost across our entire data set. So you can also do this in vector form, right? So basically you want to take the difference in your vector predictions, y, subtract it from the ground truth vector predictions, you square that, take the L2 norm, and then that should correspond exactly to computing the squared error cost function. So one thing to note here is we use capital N to denote the size of the data set. And sometimes you might see the cost function written with a n in the denominator in front, or the n sometimes goes away. I guess what's important to note here is that the argmin is going to be the same, so whatever minimizes the two expressions is the same, but then if you're taking gradients, your gradients are going to be scaled by a factor of n because it was constant. Yeah.
If you're working with a system that's relatively sensitive to the value of loss, would you just use the L2 norm without squaring it? Because any like small loss can explode.
Right, yeah. So choosing the loss function is sort of something you apply to your specific field, right? So if you think you want to penalize every sort of loss equally, you don't want to penalize things that are far away more, then yeah, you could use the norm. Yeah.
What's the B1?
Yeah, good question. So 1 is a vector of all ones, and then b is a scalar. So it's just saying we're adding the bias to each of the values.
Okay.
Yeah. So it's basically this expression up here. And then this, again, describes the trick that I mentioned before. So rather than writing out the bias separately, in vector form, we can augment our data matrix with a column of ones. So rather than n by d matrix, we have an n by d plus 1 matrix, and then you learn a weight vector, which is also d plus 1 dimensions. Okay. All right. We're going to now talk about how you go about optimizing this objective. And the goal here is we want to minimize this cost function that we defined, right? So we have some initial prediction potentially, and we want to minimize this prediction. And the key concept that we sort of want to recall from our calculus classes is the idea of a critical point. So we essentially want to find a point where the derivative is 0. This isn't guaranteed to give us a minimum of the cost function. For that to happen, you have to have a function that's locally convex in which region you care about. But it turns out the linear regression objective is actually convex. So we can go about calculating the direct solution. So there's two ways to go about optimizing in general, right? So we can either go about trying to set the gradient to 0 and solve in closed form. That's approach number 1. Or we could do a second approach, often called gradient descent. And the way gradient descent works is we compute the gradient with respect to our current parameters. We update our parameters a little bit, and then we repeat the procedure over and over again. Just because list notation with the big matrix here might be a little bit intimidating, this is basically saying it's a vector of partial derivatives. So each component is saying how a small change in Wi is going to go about affecting our cost function. Yeah.
We also need the partial K with respect to the bias.
Yes, if you're updating the bias, you do want the partial. I guess here we're secretly assuming the augmented form. We're not updating the bias, but yeah. Okay, so I think to be more proper, we should do this as well. So let's assume a bias. Any other questions? Yeah.
My question I felt right?
Yes. Yeah.
Using the iterative solution, couldn't you get stuck? Well, because you said you want to get to the point where the derivative is 0.
Mm-hmm.
If you get to the point where the derivative is 0, couldn't you get stuck at a local minimum?
Yeah, you could. It turns out the least squares objective is nice and that doesn't happen. Like there's only one global minimum. But if we're working with neural networks, that definitely becomes a problem because the objective is, in general, really complicated. You could end up at a local minimum. Yeah.
So, also want to ask, what exactly is gradient descent?
We'll cover it in a lot more detail in the coming slides. Okay. So I guess here we're considering a 1D function, which we're trying to minimize. And the idea here is you want to compute the gradient, which tells you where the minimum will be. Let's just go ahead and actually try to do this with linear regression. So it's probably best to add a page to the slides here. Okay, so we have our cost function, which is j of w, and that's equal to 1/2 xw minus t squared. Yeah. So in general, I guess it might be worth pointing out that our cost function is actually a function of the data as well, right? It's a function of x and t. But since we can't, it doesn't really make sense to optimize for the data. Like you can't change what data you're given. We only focus on taking the gradient with respect to w. But it's worth noting that there is a potential use case here where sometimes people try to optimize the data to make the cost go up, and that's the study of adversarial examples. So you can go about figuring out how you might perturb the data a little bit to make the loss go up. Like that's an interesting area of research. You can also imagine optimizing data to learn more effectively, potentially. But for this class, we're primarily focusing on optimizing for the weight vector itself. And the first identity that we sort of need when trying to take the derivative is you can, in general, write norms. Like if we have a vector A, we can write this as A transpose A. So we're going to go ahead and do that with this expression. And this is where you have to pull out some linear algebra identities. So when you take the transpose with respect to a matrix times a vector, you transpose each of the individual elements and then flip it around. So it looks like 1/2 w transpose x transpose minus t transpose times xw minus t. Does that make sense so far? So we can, in general, write out the cost function in terms of individual terms as w transpose x transpose xw. There are two terms that end up being the same. So we have a 2t transpose xw and then plus t transpose t. So this is j of w. And the main object we're sort of going to consider throughout this lecture is this quantity gradient w with respect to j of w. Any questions on the first step, like just massaging it into a matrix vector form?
I'm just curious, where did that 1/2 go?
Oh, yeah, good point. So there's a 1/2 in front of the whole thing, yeah. Sorry. Yeah. Yeah.
We're no longer requiring just a one-dimensional space. This is n-dimensional.
Yeah, this is n-dimensional case. Okay. Yeah. So yeah, I guess to be super explicit about our dimensions, it's going to be tedious to write down d plus 1, so let's just write n by d for our design matrix, right? Our weight matrix is going to be d by 1. So this is a vector that corresponds to how much we weigh each of the features. And then XW is sort of, you can think of, we also wrote this as Y on the previous slides. It's how we make the current predictions. T is going to be also n by 1. It's the ground truth vector of our targets. Right? So overall, we're going to end up with an n-dimensional vector, which we're taking the norm of and squaring. Yeah.
What is the JXT there for?
This was saying that this cost function is actually a function of x and t as well, but we're primarily just focusing on w. Like we assume x and t are fixed. Right? So the cost always depends on your data. I'm saying we just, typically when we write j of w, we just assume the data is given to us, but you should be aware that depending on your choice of data set, your cost is going to change.
What's the subscript W under the gradient?
Oh, yeah, this is just notation for saying we're taking the gradient with respect to w. Like, let's at the bottom here. Yeah.
On the top line, it looks like x to the power of 1, which I know isn't the case.
Oh, yeah.
Is that what the...
Yeah, what did I mean by that? I'm saying xw equals y. So, yeah. Okay. Any other questions? Okay. So, can someone tell me how you would go about taking the derivative, or sorry, the gradient of this first term with respect to w? So this term here. There's a reason, I guess, we did the math diagnostic. Like this term is gonna, should sort of look familiar. Yeah.
Is that going to end up being 2x transpose xw?
Yeah, great. So if you remember from before, x transpose x is just some matrix here. It's, I guess x transpose is d by n. Let's write out dimensions. X transpose is d by n, and x is n by d, right? So what that means is when you take the product of x transpose x, this is actually a d by d matrix. So it's a square matrix. And then on the diagnostic, we basically made you solve the gradient in this particular case, right? And we called it A. So the gradient with respect to W transpose AW is 2AW, right?
That's only if A is symmetric.
Yeah, so in this case, X transpose X is symmetric because if you take the transpose, you just get X transpose X, yeah. So what that means is for this first term here, we're going to get 1/2, take the gradient 2 X transpose X W. And then this second term here, it's slightly trickier, I guess, but maybe because you haven't seen it before, but you can think of this T transpose X as, let's write dimensions out again. So whenever you get confused by vectors and matrices and what the dimensions are, just try to write out the dimensions of different products, and that can help you become unstuck. So I guess it's helpful when lecturing as well. So if you have W, which is d by 1, T transpose X, so what's the dimension of T again?
N by 1?
Yeah, T is n by 1, so T transpose is 1 by n. And then X is n by d, right? So T transpose XW is a 1 by d times a d by 1. It's just a dot product, which means the output is a scalar number as well. And in general, the derivative of C transpose W is just going to give you C itself. this is something you should confirm to yourself later on. It's also, I think, described in more detail in one of the lecture readings. So what that means is we're going to end up with a 2x transpose t term. And then what's the derivative of gradient of t transpose t with respect to w? It's just 0, right? Because there's no w, so that term goes away. So we're left with, let's move this here. You can just cancel out the 1/2 to write it out a little bit nicer. We have x transpose x w minus x transpose t. So that's a value, that's a gradient expression. Yeah.
Sorry, I thought the second term was going to be a 1-by-1 matrix because of the fact that you're doing 1 by m and n by b, then b by 1.
Yeah, 1-by-1 matrix, I guess you can interpret as a scalar as well, right? Yeah. So it's dimension just 1.
Exactly.
Yeah.
So then you're doing the derivative and getting rid of the w term, but I don't know why that makes it x transpose t instead of t transpose x.
I guess it's mainly because of the convention we follow in this class, which is that the gradient is the same dimension as the vector itself. So what I'm saying, I guess, is if we have a function in general that goes from Rn to R, we're assuming the gradient is going to be n by 1. Yeah. Yeah. But in some areas of math, you'll see the transpose notation. So the transpose is just making the dimensions work out correctly. Yeah. Any other questions? Okay. Yeah, this is something that could be beneficial to work out more slowly later on, like to try to replicate this by yourself. And I think the third problem on the homework has a similar derivation you have to carry out for ridge regression. Okay, so to not lose the forest and the trees, what we're trying to circle back to is we have this gradient expression, and we can try to solve our linear system directly by setting the gradient equal to 0, right? And then figuring out what w is. So if we go ahead and do that, we have, we just set this expression equal to 0, and then try to find what w star satisfies this equation being equal to 0. So if you rearrange the terms, we get w star has to equal x transpose x inverse times x transpose t. This term here is often called the pseudo-inverse because it's something you can use even when x isn't a square matrix. So if x is a square matrix and invertible, it's going to reduce exactly to the inverse. But in general, our data matrices aren't going to be square, right? So this is sort of saying you can approximately have a notion of the inverse by computing this expression here. Okay. And this is yeah, go ahead first.
You also need the determinant of x is non-zero then, otherwise inverse doesn't exist, like of the x transpose x.
Yeah, I think x has to be full rank for this to work. Yeah.
Can we guarantee that always?
You might not be able to, yeah.
Okay.
So, yeah, this is one potential pitfall of trying to solve it directly, right? Like, so you have to. Yeah. But the fact that there is a closed form solution is a pretty nice property because for many of the other algorithms that we'll discuss, including neural networks, you won't be able to write down a nice, relatively simple expression that tells you what the optimal weights are. Okay. Yeah. Did anyone else have any comments or questions? Yeah.
What if X transpose X is not invertible?
Yeah, if it's not invertible, then we have to resort to other methods to solve the system. Namely gradient descent, which we're talking about next. Yeah.
Sorry, could you go back to what W was a couple of slides ago?
Oh, like what W is here?
Yeah.
Yeah. W is a weight vector that tells you what essentially how each feature is going to affect the output that you're trying to predict. So this whole process here is we're trying to go about finding the W that minimizes the objective. So how do we find a W that minimizes the squared cost? Okay, so the more general solution is, which tends to always work, is, well, I guess not always work, like it'll get you to a critical point, is something called gradient descent. So I guess the canonical picture you might sometimes see is you have some contour graph, and these are your weights. You should sort of imagine this as a bowl-shaped function. So we're actually picturing something that looks like this, and the contours are basically the points that are equal loss, right? So this is something you often do when you go hiking or something and you see a map, you'll see the contour lines like of equal elevation. And what gradient descent is saying is we have some position we're currently at, and we know how to take gradients. The gradient is the direction of steepest ascent, actually. What we want to do to minimize the cost is go in the direction opposite the gradient, right? So we're going to try to go in this direction. And then after you take a step, you have a different loss because your weights have changed. Then you go ahead and compute the gradient again. And it's always like the direction of steepest descent, right? So we just continue going downhill. And I guess this hill climbing analogy is super ingrained in people's minds because whenever you go hiking with machine learning people, they'll make gradient descent jokes. But yeah, I guess it's a good way to build intuition.
Sorry, will there ever be a case where you do a gradient descent and just go around in circles because that's exactly how planets are orbiting?
Right. Not in the linear regression case if you pick a good learning rate, but there could be potential more complicated loss surfaces where gradient descent, I guess, doesn't hit the exact minimum. But it works very well in the case of linear regression. So I guess we're just going to go ahead and use this gradient quantity here that we derived on the previous slide again and again. So it's X transpose X W minus X transpose T. And I guess like when you work through a derivation like this, it's sometimes useful to get some intuition on what these terms are saying. So what actually is XW minus T? Like, can we interpret what XW minus T is saying? Yeah.
The difference between the prediction and the true value.
Yeah, exactly. So this is prediction minus true value. And the intuitive way to think about this is if our predictions are really far off from the true value, then the gradient is pretty large. It's saying if we make a relatively small change to our weights, we can get a big change in our loss objective. But if we're approaching convergence, like we're getting close to where the gradient is 0, then that means our predictions are also relatively close to the true value as well. Okay, and yeah, I guess there's some slightly nicer visualizations here on what's going on. So you can picture both 1D and 2D loss functions. And gradient descent in general is corresponds to following this update rule for each of our weight components, right? So this is for one single component. In general, we want to update all the components simultaneously. We don't care. We care about all the features, not just one of them. And it corresponds to walking down towards the point of lowest loss. So I guess one interpretation, if you focus on a specific component, is if you say that the partial derivative with respect to Wj is positive, then if you want to decrease your cost, then you have to also decrease Wj. But I guess the geometric picture is really what you should be picturing in your head. Like gradient is pointing in the direction that increases your loss, you want to go opposite that direction. Yeah.
What would you do if there's like not in this one, because like this one's just a quadratic, so of course the gradient is going to exist everywhere. But let's say in a more complicated example that let's say the gradient vector field is actually not smooth, so like there's an edge at some point. So what do we do there?
Yeah, that's a good question. I think for most of the cases in this class, probably all of them, we assume we don't run into such problems. But then you could imagine like non-gradient based methods as well. Like you can randomly perturb your weights a little bit, which doesn't require taking any gradients and just seeing how your loss changes. It can also help you estimate how you're making progress. Yeah.
How do you choose small and alpha?
How do you choose alpha? Yeah, that's something we'll talk a lot more about in future lectures, but I think there's a slide about it soon. Yeah.
So what is the criteria for us to stop alpha?
Yeah, that's also a good question. So you can plot essentially what your loss looks like over time, right? And typically the way we decide to stop is we look at a training loss or a validation loss, and it'll sort of look something like this, where on the x-axis you have iterations, so how many steps of gradient descent you've run, and then on the y-axis you have the loss, which is L or J in this case. And eventually you're going to get to a stage where you sort of plateau. In that case, you can consider dropping the learning rate or just stopping when your loss hasn't been improving for a while. Yeah, in fact, here's some guidelines for how you might go about setting the learning rate. So I guess learning rate is sort of a trade-off, right? You want learning rate to be large so you make as much progress as possible. But if you set your learning rate to be too big, you're going to get to regions where your gradient is no longer accurate, right? So in this 1D visualization here, if you set your learning rate to be really big, you might overshoot the minimum completely. This is actually okay in this case because we're making overall progress. But if you go way too big, then you can end up on the other side and blow up. So you don't want your learning rate too big. You want it to be like small enough such that you're still making incremental progress. Yeah.
Could we like iteratively increase alpha over time as well?
Yeah, that's a common strategy actually. Yeah, there's a bunch of research and strategies on choosing learning rates, but I think a good default is just try a reasonable value like 0.01 and see if you're making progress. If you are, you could increase it a little bit more. If you aren't and it looks like your loss is exploding, then you probably want to decrease your learning rate. One additional note here is, remember before that sometimes you write the loss with the n term, so the n is denoting the number of training examples. If you have that n term in your loss expression, it ends up scaling your gradient as well. So your learning rate needs to sort of account for that as well. We can write our update rule in vector form, so you can write this as w equals w minus alpha times this gradient term. I've been writing this as gradient W, J of W, but either way is fine. And for linear regression, I guess I wrote down the vector interpretation a bit earlier, x transpose times xw minus t, but you can also interpret the gradient in summation form if that's easier as well. So x transpose times xw minus t should be equivalent to this expression here. And another way you can measure whether you've converged or not is you can check if the gradient is close to 0. So if you hit a critical point, your gradient is 0, right? So as long as you're computing the gradient, you can use that as a measure of progress. Next logical question is like, why do you use gradient descent? So it's applicable to a much broader set of models. It's oftentimes easier to implement than direct solutions because many of the machine learning libraries you work with are able to compute gradients pretty efficiently. And then when you're working in high dimensional spaces, it's oftentimes could be, even though you have a closed form solution for linear regression, it's still potentially more efficient to use gradient descent. And the reason that is when you solve for the linear regression solution, you're computing this term x transpose x and taking the inverse, which is an O of d cubed operation. Whereas for each step of gradient descent, we're computing x transpose xw minus t, right? This is just O of n times d operation. So we can potentially do a lot of gradient descent steps for one linear regression, like computing the direct solution. Okay, any questions? All right, I think feature mapping sort of ties in more nicely with the next set of topics, so we can take a break until, let's say, 12:10, and then resume then.